Hello world, this is Craig. Let's talk more about the assembly for the 8008, and we're going to start today by looking at the syntax of a line of code. So this is our line of code where we left off last time. We have our label, which ends with a colon, and then we have some white space, and then we have our code, which is going to be our mnemonic, more white space, our operand, white space, semicolon, and a comment. Okay, so for the label, either uppercase or lowercase is probably okay. It depends on the assembler. And there's likely the assembler may even ignore the case, but if the assembler does differentiate between upper and lower case, you have to remember that you have to then be consistent in your labels. So for example, if you have a label called start and you capitalize it, so capital S-T-A-R-T, if you later refer to that as start with a lowercase s at the beginning, you're going to it's going to throw up a undefined label error. So you need to be consistent in how you do your labels. So the assembler will probably allow the first character in the label to be anything other than a number. And the label itself can't be from the reserved list, and the reserved list is basically anything that you would find in the code or anything that you would find in an expression. So you can't have, for example, any of the register names, you can't have any of the Boolean logicals like an and or an or. Those kinds of things can't be in the label, but there's quite a bit of freedom with what the label can be. Just don't try to start that as with a number. The white space can be any number of spaces or any number of tabs, so there's no restriction on that. The assembler will probably require that the label starts in column 1, and it will require that the code starts in any column other than column 1. Just put your labels starting at the very left side in column 1, and then when you're doing a code, at least put in one space before that. Other than those requirements, the assembler is fairly lax in terms of the syntax, as long as you're using a valid code and the valid number of arguments in the operand, and you use your semicolon, and after your semicolon you can use any character you want after the comment until the end of the line. For the code mnemonic, the assembler is probably case agnostic. It doesn't care whether you use uppercase or lowercase most of the time for the code. Now you can't use bracketed comments like you can in C, where you would do a slash asterisk and then have as many lines as comment as you want, and then you would end that with the asterisk and a slash. You can't do these block comments. You can only do a comment per line, but there's no requirement that you have any of these things before that, so you can start a line out with a semicolon and have the entire line be a comment then after that semicolon. Okay, so that's about it for the syntax for an instruction line. Okay, so let's look at our memory again. We're going to revisit memory so we can better understand that. When we are addressing our memory, and we're using one of these little EPROMs, like this is the 1702A, this is one of the first EPROMs. So we have 8 bits in our address in this EPROM. So if we have 8 bits, we can have 2 to the 8th combinations, or 256 combinations. So we can have 256 different addresses in this EPROM. So the EPROM will start at address 00000000, and it'll go on up to 11111111. And if we looked at that in decimal, this would be address 000 in decimal, and this would go up to 255 in decimal. That's our 256th location because we started at address 0. In octal, 000, and we would go up to 377, or in hex, we would start at 00 hex, and we would go up to 0FF in hex. Those are all the addresses that this EPROM can have, and of course in each of those addresses there's 1 byte of data. So we have 1, 2, 3, 4, 5, 6, 7, 8 bits that are in each of those addresses. Since we have 8 bits wide and 256 bits long, that means the total number of bits in here are 256 times 8, or 2048 bits, or this is what we would call a 2K bit So this holds 2 kilobits. Okay, in our MIL-MOD, how do we address this? Well, we have 14 bits worth of address. And so we have 2 address bytes. So we have our high byte and our low byte. And we already said our low byte is going to be the addresses that are in this. And so, for example, our low byte is going to go from 000 up to 377 in Octal. So those are the low byte. Those are all of the addresses in this one chip. So the high byte then is left over to allow us which chip we're going to access. So let's say that this is chip 000, and we've got another chip here. We have another chip, let's call that 001. This guy's 002, and each of these are going to go from 000 to 377. So in other words, the very first address in this one is going to be 000 up through 000 377. If we add 1 to that, we go up into this page. And so our higher address then goes to 001. So the first address in this is going to be 001 000, and that's going to go up to 001 377, and then the very next one is going to be 002 000 up to 002 377, and so forth. Now, because it was common to use these chips in these systems, they came up and they started calling the high address, or which EEPROM is being used, as the page. So they would call this page 0, this page 1, and this page 2. So in a lot of the documentation, you'll see where they reference a page. The page is simply the high byte of the address. And it was common because when you were writing programs, you would do your best to keep a certain section of code or a table or some data within one page. You would try to keep it, you would move things around so that you could have things in a fixed page. And the concept of a page didn't go away even when we went with more modern, larger processors. If that processor can't address everything at one time, all the memory at one time, we would break the memory down into pages, and so you would page swap out memory. This is the same kind of thing. You would have different pages that you would address, and that page is kept in the high byte of that address. Okay, well, the reason I told you that is because I haven't been completely honest with you in terms of the HL register. So let me move this out of the way. Okay, well, it's not that I haven't been honest, it's just that I haven't told you about how the HL registers are actually used. A, B, C, D, E, these are just general purpose registers. Of course, this is our accumulator, it's the workhorse, it does most everything, and then we have B, C, D, E, just general purpose use. We can also use HL as general purpose use. But the reason HL have a different name, they're not just called F and G or something like that, is because the HL stand for high address and low address. Because the HL address, or the address contained in the HL register pair, is actually a pointer to this memory location. We call this a memory register, but it's not really a register. It's just an area out in memory. It's a location out in our memory. So while these are all general purpose registers, the HL pair work together and control which memory location is being pointed to whenever we use the M register. And again, the M register is not really a register in the processor. The M register is just a memory location, and it's the memory location that's pointed to by the HL pair. So that's why they're called HL, for the high byte and the low byte of the memory. Okay, so for example, if H was equal to 001 and L was equal to 005, the contents of the memory location 001, 005, so it would be in this page 001, 005 would be the memory location that is being pointed to, and so that has some value in that, and that value is equal to whatever we get or whatever we put in when we use the so-called M, or the memory register. So what that means is that we have to know what HL are, or we have no idea which memory location we're pointing to, and so we have to set up the HL pair so that we know where the M register is addressing. So this is a little segment that I call Future-Proof Your Knowledge. In the 8008, all of these registers are independent. In other words, we can't increment them as a register pair. So even though this H refers to the high byte and L refers to the low byte of the address, when we get up to 377 in the low byte and we increment L one more time, it doesn't automatically go up and increment H going into the next register. But when they put the 8080 on the design board, they realized, let's treat these registers, H and L, as a pair. So we can do some things as H by itself and some things as L by itself, but we also have new instructions that we can control H and L as a pair. For example, we can increment HL as a pair, which means when we increment them as a pair, when L gets to FF, or when it's about to roll over and we add 1 to it, it doesn't just go to 0 by itself. It goes to 0, but then H increments by 1. And so it's much more convenient to be able to address these as a pair. While they were doing that, they went ahead and they put BC as a pair and DE as a pair. So when we start looking at the 8080 again, there's a lot of instructions that work on registers pairs. And those added a lot of value to the 8080 to be able to handle these things in pairs. Okay, let's write a program. For many decades and all of my life, the first program that you would write whenever you get a new piece of hardware or a new processor, a new operating system, or a new display or something like that, you would write the Hello World program, which outputs to the teletype or the paper tape or to something, the display, the words Hello World. So when we do Hello World, this little program, this is what we're going to do. We want to output the 15 characters. And so the 15 characters we're going to output are a carriage return and line feed. Then we're going to output hello and a space and world, and then we're going to output another carriage return line feed. So this will put the hello world on its own line. Okay, these are the steps we're going to do for our hello world. First thing we're going to do is set the HL to the location of our starting text. So we're going to have a table, and in that table we're going to have the characters for hello world. And the first thing we have to do is set our HL register pair to the beginning character in that hello world so that when we get something out of memory, we're actually pointing to the first character in our table. So the first thing we're going to do is set up HL to our text starting location. We're then going to set up a counter. We could use a delimiter, like maybe an exclamation point or something. And so when we got to the exclamation point, we knew that we were done outputting this character string. But instead, we're actually just going to use a counter. We're going to output the 15 characters. So we're going to set up a counter and count that down with each character. Now we're actually going to have our loop. When we have our loop, we're going to get our character, and then we're going to send that character out to the teletype, or in this case to the terminal program that we're using. And we will use a routine that is already built into the Monitor 8 program. So we'll get that character, and then we'll output that character to the teletype using the resident monitor. We then increment HL so that we point to the next memory location, and we will decrement our counter because we got one character done. Okay, so we will increment our HL, and then we will decrement our counter, and then we will check our counter value. If we're at the very end, if we've output all of our 15 characters, then we're done. And we'll finish the program and return back to the monitor. If we're not done, then we'll just loop back up and we'll get the next character, output it, increment to the pointer, decrement the counter, and then loop. Get the next character, output it, so forth. Okay, so that's what we're going to do with our program. So this is actually our program. We're going to print hello world to the teletype. We're going to use the resident monitor to do the actual character sending, so we don't have to worry about how to send something out of this MIL-mod system. The monitor prints ASCII whenever a restart 020 is called, and the character it's going to print has to be in register B. So we put our value in register B, then we do a restart 020, And then that hands it off to the monitor, which sends it out. And then when the monitor is done with that, there's a return that kicks it back to our program. Okay, we're going to start our data at the address 010.250, and we're going to start our program at 010.200 because the monitor 8 and the monitor 80 have a bunch of register or of memory values that they use for buffers, and so we want to be up above all of those memory values. So where our memory actually starts, our RAM starts at 010.000, we're going to give the first bit of that to the monitor, and we're going to start our program at 010.200. So let's actually write this program, and we're going to at first do this by hand assembling. So I have this little form that I use when I'm hand assembling, and let me go ahead and fill some of this out. The program name is Hello World. So when we fill this out, the first thing we do is we write our little program codes and labels and operands over in these columns, and then we'll fill out the data over here on the left. The first thing that we want to do is load in the register E immediate the 015 decimal, and this is how many characters we're going to output. We're going to put our counter in register E. The reason we're using register E is because later when we use the routine in the monitor 80 that sends that out to the teletype, it destroys registers A, B, C, and D. The only registers it doesn't destroy are E and the HL pair. So we will put our counter in E so that it doesn't get destroyed every time that we call the teletype output. Next thing we want to do is load into H the page, which is going to be 010. We're going to load in the L the offset of where we're going to start this program, and that's going to be at 200. Now we want to start our loop. So this is, let's call this our loop. When we start our loop, we want to get our character, and so we're going to load register A from whatever is in the memory. And the memory, of course, is what is being pointed to by the HL pair, and hopefully that's going to be our first character. So LAM loads into A whatever value is in memory M. And so we're going to get the character. Now the teletype output requires that the most significant bit is set. So we're going to OR immediate. So we're going to OR immediate with a 200 to set that most significant bit. So the restart 20 requires the most significant bit to be set equal to 1. After we set that bit, we're going to load B with A. So we're going to move our character from register A into register B where it has to be for the teletype output. Now everything's ready. We have the character in register B. The first or the most significant bit has been set. So now we can call the output routine. And the way that we call it, instead of a call, we're going to do a restart. And it's restart 020. So remember, a restart is that special call that we don't have to put the address in. It's a predefined address. So when the program gets to this point right here, what it's going to do is put the program counter for the next instruction on the stack, and then it's going to replace the program counter with this value, this address. And so that program is going to go to that address, execute whatever code it takes to output that character, and then that code will end in a return of some type, maybe a return or a conditional return. When it gets to that return, it's going to pop that program counter back off of the stack, and that program counter is going to be this instruction right here. So it'll come back, when this is complete, it'll come back to this next instruction. And in this next instruction, we're going to increment the L register, which is our pointer. So point to the next character. We're going to decrement our counter, so DCE. And now we're going to look at our counter. We know that the DCE sets the flag, so we're going to jump if there's a false 0. So in other words, if we're not equal to 0, if E When we did that decrement would set the flags, and if that decrement dropped E to 0, it would set the 0 flag. But if it's not 0, then we want to loop back up and do the next instruction. So if it's not 0, we want to go back to loop. So we want to do this until done. If it was 0, it'll fall through this, and then we want to do a safe restart and return back to the monitor. Okay, so let's load our program again. We're going to load into the E our counter of 15. We're going to load the HL register pair with our address, which is 010. This isn't, we didn't want to load 200 here. We wanted to load 250 because that's our data. That's not our program start, that's our data start. Sorry about that. We then want to move from the memory into register A, so we get our character. We then OR that. We set the most significant bit to a 1. We then put it from A back into B, and then we call our restart 020, which will output that character, and it will return back to the next line, which will increment to the next character, decrement our counter in E. If our counter is not equal to 0, it will loop back up and get the next character. If our counter is equal to 0, it'll fall through and do a restart and return back to our monitor. Okay, so this is our program right here. Now what we do is we convert that using our table. So using our little chart here where we get our opcodes, we'll convert that over into binary. So the LEI, looking at our table, LEI is, the instruction is 046, and the data is, it's not 015 decimal because this has to be an octal. So it's 017 in octal. LHI is 056, and its data is 010 in octal. LLI is 066, and its data is 250. LAM is load A from M is 307, and there is no data. ORI, so the OR immediate, is 064, 200. And so you can see, remember my warning in the last video about forgetting your data byte. You can see how you just put that in and you forget the data byte, go on to the next one. LBA, so load B with the value in A is 310. Restart 020 is a 025. Increment L is 060. Decrement E is 041. Jump on a false 0 is 110. We have to put in the address that we're going to jump to. So once we come here where we need an address, now we're going to go over here and start filling our addresses in. Well, these are all in page 010. We start at line 200. So 200, 201, 202, 203, 204, 205, 206, 207, 208, 209, 207, it's not 208, it's 210, 211, 212, 213, 214, 215. So this is 215, 216, 217, 220. Okay, so the address that we want to jump to is 010, 206. And remember, this is Little Endian, so this goes in as 206010 is the address that that's going to jump to. And the restart 000 was instruction 005. Okay, so these are the values that we would put into our processor, into our RAM, in order to run this program. And these are the addresses that those are going to be at in our RAM. Okay, now we need to have our data. So we're going to have our data, and we're going to put our data at same page, 010, but we're going to start at memory 250. Okay, and so let's put in 1 byte per line. So this first one is going to be a carriage return line feed, 015, 012, that's a carriage return line feed. H is 110, E is 105, L is 114, 114, 117, and then a space is 040. So this is a carriage return line feed, HELLO, and then a space. And so there were 8 characters there, so this is going to take us to 260. 260 is going to be a 127, 117, 122, 114, 104, and a carriage return line feed. Okay, and so this is WORLD, carriage return line feed. And so that ends at 260, 1, 2, 3, 4, 5, 6. So 266 is when that last one ends. So 260 to 266. Okay, so that's all of our data. Okay, the segment again, future-proof your knowledge. As soon as Intel got the 8080 on the drawing board, they realized that maybe they made a mistake in some of the decisions for the 8008. So the 8008 has 2 sets of mnemonics and 2 ways of putting these in, so 2 syntaxes. This is the old set. There's also the new set, which look much more like the 8080 instruction set. So when I'm programming 8008, I intentionally use the old set, and when I'm using the 8080, then I use the new set. But just so that you know, you will see some 8008 code that has the new mnemonics, and they were just put out, and assemblers were put out to support the new mnemonics in order to make it look more like the 8080. Now, if you do hand assembling, one thing that you may want to do sometimes is throw in a no-op, so that when you key all this in and you realize that you forgot to have a certain step, you can come back and get rid of your no-ops and put in actually instructions. So sometimes it's worth putting in some no-ops in here, or just a forward jump down a few bytes, so that if you have a really long program that goes pages and pages and pages, you can put in these no-ops or these forward jumps so that you can come back and have little breaks. Leave yourself 10 bytes every now and again so that you only have to move so much code. So now let's put this program into our Mod 8. Here's our terminal window that we're talking to our Mod 8. We're running the Monitor 8 on this, and we press a restart and we get the sign on, which is just these dashes. Okay, let's load our code in Octal. And the way we do that is we type the LDO. It asks where do we want to start. We want to start at 010, 200, and we want to go up through 010 to 20. Okay, now it's saying, okay, let's go ahead and go. So we do our slash and a space, and now we can run through and put our code in. So the first is the LEI, that was a 046, 017, 056, 010, 066, 250, 307, 064, 200, 310, 025, 060, 041, 110, 206, 010, 005. Okay, and that's our program that we just put in. Now, we could have put that in symbolic. Let's go ahead and dump that symbolic. So DPS, dump symbolic, 010, 200, 2010, 220. Okay, let's look at our program here. Here's our LEI 017, LHI 010, that's our page, and LLI 025, That's a mistake. We got to change that to 250. LAM, load A from the memory, then OR that to set the most significant bit, and then load B from A, restart 20, which will output that, and then increment L, point to our next character, decrement E, that's our character counter, decrement that. And if we have a false 0, we want to jump back up to 010206, which 010206, that's where we get the next character. So that's correct. And then we do, when we're all done, we fall through that JFZ and we do a restart 0. So we have to go back and change our that 010204 from a LLI 025 to a LLI 250. So I'm going to put that in as a LLI 250. Okay, now let's do a dump symbolic. Great, so our program looks like it's all there. Now let's load in Octal our data, and we're going to put our data at 010250 to 010. Our last one was 266. That's where we're going to put all of our data. So we put in our slash and our space to start with. So here goes our data. Now let's check to make sure that that got in there okay. Let's dump Octal 010250 to 010266 and let her go. Carriage return line feed, that should be a HELLO and a space, WORLD, and then a carriage return line feed. Okay, so proof's in the pudding. Let's go ahead and run this thing. XQT 010200. Hello world. All right, so there's our program. We ran it. Now let's do that with the assembler. So let's actually go ahead and get the assembler. We go to Herb Johnson's website, which is retrotechnology.com, and we're looking for A08, which is an 8008 cross assembler. We can click on this version right here, and that takes us to where we can save the file. So we go ahead and save the file, and it downloads as a zip. We unzip it and put it in whatever folder we want. So when we unzip it, we can see that we have all of the source files here, and if we wanted to, we could go ahead and modify this and go off and make our own assembler if we wanted, or we can just use Herb's because he takes pretty good care of it. Two files that we're really interested in are the A08 documentation and the A08EXE. That's the assembler. There's also a few other tools in here, and there's some sample files, but those are the two files that we're most interested in. So what I'm going to do is we're going to take those two files and we're going to copy them into our working directory. So let me go ahead and copy those. And let's go over to our working directory and paste them. This is our working directory where we've got the documentation, we've got the assembler, and then I've created a text file called hello world.a08, and this is our text file that we're going to, this is our source code. Let me go ahead and open that text file. Let's take a look at that. All right, so here's some documentation at the top. Hello world outputs to the milmod 8 teletype using the monitor 8 restart 20 routine. It reads data from the table using preloaded character counter. Restart 20 destroys registers A, B, C, and D. Mentioned earlier, these are all comments. They begin with a semicolon and they cover the entire line. We then have a little decoration here. We've got a comma, and then this marks our program. The assembler understands the following. It understands labels, and here's a label that's called loop, ends in a colon. We already mentioned those. It understands expressions, so you can do things like addition when you have a variable in here. And for example, rather than loading this 015, we could have loaded 010 plus 005, and it would have added those two together and created the 015. So it understands expressions. It understands numeric constants, and we can use the base identifier. So here I've used decimal. I've also used octal in places, but we can use binary. We can use O for octal, or we can use H for hex, And we can use those in upper lowercase usually. If we don't put anything in, it's probably going to presume that that is a decimal value. And if we are using hex, we have to remember that we have to start that with a 0 if the first character is a letter. So instead of FF hex, we would have to put in 0FF hex. It also understands string constants, understands the machine opcodes, obviously, but it also understands assembler directives, which are also called pseudo opcodes. So at the very beginning of this program, we have one of these pseudo opcodes. ORG is not an instruction that the 8008 understands, or the 8085 for that matter. Nobody understands that ORG except the assembler. What ORG says, where is the origin of the code? Where does this code originate? Where do I set the program counter to when I start assembling this code? So we have told it that the origin or originate this code with the program counter 010200 in split octal. We could have put that in hex or decimal or whatever value we wanted. Fortunately, this assembler, Herb, has this, so it takes split octal. And that's one of the unique things about this. You might find these old assemblers other places, but this one that Herb has is the only one that I have found that takes values in split octal and then will give us values in split octal. So it's very convenient to work with the mod 8 because this guy already works in split octal. The next thing we have is just our program. So we have load E immediate 015 decimal, load the HL registers with our page 010 and our memory offset 250. We have our label, which is loop with the colon and the LBM instruction. So the load B, I had a mistake earlier, so I have to change this from LBM to LAM. I forgot that I had to set that bit to 1 in the A register, and so let's do it LAM OR with 200 to set the most significant bit, and now I'm going to LBA, put that into register B, for the output. We then call the output routine using the restart 020, increment to the next character, decrement the counter. If it's a false 0, we loop, and if it's not a false 0, then we reset and go back to the resident monitor. We then have another little decoration and our data table. So again, we've used the ORG pseudo opcode or directive, assembler directive, and we want now the program counter to be at 010250. There's another assembler directive or pseudo opcode called the DB or a data byte. What that allows us to do is simply splice in bytes into the object code. So we put a DB, and then you can see this is our carriage return line feed, hello world, and then a carriage return line feed. Then the final assembler directive or pseudo opcode is this end. The assembler has to know when this program is over, and so we have to put the end. And one thing to note is that the pseudo opcodes, the org, the DB, and the end, those can't be in column 1. Those need to be somewhere besides column 1, just like any other opcode. All right, so we go ahead and we save this, file, save. And now we open a command prompt and we go to that folder. So here we are, users, Craig, documents, hello world. And these are the values, these are the files that we have in there. We have the assembler documentation, the assembler, and our program. So the assembler is done on the command line, and we will do A08. We give it this, that's the name of the assembler, so the program that we're invoking. We have to give it the source file. Our source file is hello world, and we have to give the extension A08. Okay, now we're going to hit the return and see what it does. Okay, it said no errors. Well, that's great. We know that it has no errors, but it has also not given an output. There's no more files in there now than there were before. So what we have to do on our command line, let's go back to our same command line, where we're going to add, we have the A08, which is the program we're invoking. That's our assembler, hello world. We want it to make a list file. And the list file, we're going to call it hello world, LST. We also want it to make an object file or an output, and we're going to call that hello world, HEX. Now this assembler, the output, the object file that we talked about when we were talking about the various, the complete process, I said the object file could be a hex or an octal or a binary, but for this assembler, the object file is always going to be a hex file. Okay, so we know it's going to assemble. There's no more errors. It opened the file, and now if we look, it has created two more files. There's the list file and the hex file. So let's look at the list file first because that's the most satisfying. So here's our list file. Look at this. Here is our original code. So all of this just got passed through. Here's our comments. This is all just our original code over here on the right-hand side. But over on the left-hand side, look at what we've got. These are our memory addresses where our program is. So this org 010200, we can see that the program counter here is at 010200. So that sudo opcode moved our program counter to 010200. Here our instructions start. First instruction is at 010200, and this is our instruction, 046, and this is our data. So we had this in as decimal, 015 decimal, and it converted it over to us, for us, to octal. Next memory address is 010202. Here's our instruction 056 and our data. 204, 066 is our instruction and our data, which is the low byte of the HL register. So that's the 010250, which is where our data table is. 307, that's load A from M. And then here's our OR immediate. There's our data for our immediate. 310 is our load B from A. So here we move the character into B. We then call our restart 020, which is going to output it. We increment the HL pair. We increment the L, I'm sorry. We decrement our counter, and then we loop. So 110 is the jump if a false 0, and it's going to go to the address 010206. Remember, this is in Little Indian. It does that loop until the counter has gone down to 0, at which case it'll fall through this loop and do a restart 0. In other words, return back to the monitor. So here's our data. Carriage return line feed, HELL. I'm missing a L here. Okay, so let me save that. Now let me reassemble it. HELLO space WORLD. Carriage return line feed. So here's our program. If we wanted to, we could just take these values and put it into our mil mod just like we did before. Eventually, of course, we'll put this in an EEPROM and move it over to the mil mod, but for right now, we could hand code this in. Before we leave this, let's look at a few tricks. The data byte is actually more powerful than having to put these bytes in individually. It can understand ASCII strings. So we can replace all of the hello world with a quoted ASCII string. So we have a carriage return, comma, line feed, comma, hello world in quotes, comma, carriage return, comma, line feed, comma. Let's save that. Reassemble. Still no errors. So let's open it up. And we can see that now it's taken this carriage return line feed and all of these ASCII characters and then a carriage return line feed, and it has spliced that into the code. So it took care of that for us. Okay, so that's one little trick we can do. There's another little trick we can do, and that is that it's easy to move something and then forget what memory location we put it in. Let's give our table a label. Let's call that table. Now that table has a label that we can reference, so we can reference that program counter, and we're going to use that to put this in for the HL pair. Now we can't just say load H immediate table because this table is going to be a 2-byte value. But what we can do is we can use an expression. And the expression we're going to use is high. We're going to take the high byte of that value table and load it into H. And then we're going to take the low byte value of table and load that into L. Let's go ahead and save that. Reassemble. No errors. Open up our list. And look at this. It has taken the high of that address. So here's table, and here's the value that it gave table, 010250. And it actually tells us down here at the bottom, these are the addresses of our labels. Table is at 010250. It then took the high byte and loaded that into H, like we asked it to up here, 010. Took the low byte and loaded that into L. So now we don't have to worry exactly where we put our table. It's all automatic. Wherever we put this up here, it will automatically find it. And we can do that one better. We don't need to put an org statement as to where we put that table. We can just have it follow our data. So let's go ahead and take that org statement out. Now after the restart instruction, it'll immediately go into the table. Save that. Reassemble. Open it up. Instead of being at 010250, it's just immediately after the restart 0, the table data just bumps right up against the bottom of our program. So from now on, because we used a label here to put where the table was, and we used the high byte, low byte trick up here, we don't even have to worry about where that table is. We can do one better than that. We have this 015 that we have to keep track of. That is the number of characters in our table. Okay, so let's do a little trick here. Let's create a variable called table length, and that is going to be equal. So we have the assembly directive EQU, which means equal, and we're going to set that equal to wherever the program counter is now minus the label table. So whatever the location of the label table is. Let's go ahead and save that. Assemble. Look at the output, the list file. And it has given us this table length, which is equal to wherever the program counter was. And so the program counter, when it got to this point right there, was 010236. So this was at 010236, and it subtracted off where table started, and that expression gave us the value 017. Okay, so now we have a variable called table length that is 000017. Okay, and since it was a subtraction of two different addresses, it's a word long, so it's 2 bytes long. But what we can do is we can take just the low byte of that and put it in place of that. So let's do low table length. Save that. Reassemble. No errors. Good to see. Open it up. And now we have, here's our low table length. And so it has given us that value instead of having to hard code in the length of that table. So we're going to change this to, we don't want to make a change in our list file because it's not going to save it. But we can make the change back over here. We're going to output, we're going to change this to load register E with the length. Okay, so that's automatic. So you're getting the idea that once we start getting into the assembler, we can make things so easy for us to change. We can make all these things automatic, so we don't have to worry about so much of this information. We let the assembler worry about that. You can also go to Dave Dunfield's website, which is classiccmp.org, classiccomputers.org, and he has down here at the bottom, you can see his own Mod 8 simulator. So you can download the simulator. It only runs on, it won't run on a 64-bit machine. You have to run it on 32-bit or less. But you can download this simulator, and we'll do that next time and play with this code. Okay, so that's it for this video. I thank you for watching. Hope you enjoyed it. And if you have any comments, let me know. Thank you. Bye.